We move on to power. Power is the rate of energy production or consumption. When we say rate, definitely this means we need to divide by time. So power, we define it as energy per unit time. Energy or work per unit time. The unit is joule per second. This unit, joule per second, is called watt, honoring James Watt, the guy who invented the steam engine. So in the SI system of unit, he was honored by naming the unit of power after him. Okay, so don't mix things. This W here represents work. This W here represents the unit of power. Okay, usually units will follow the numbers, the numerical answer. Okay, so in general, we know that work equals F delta X by definition. So the average power, now if you substitute for work F delta X divided by delta T, delta X by delta T is the average velocity. The average velocity, right, as we learned in chapter 2. So from this, the average power can be calculated from the product of the force by the average velocity. Average power is equal to force multiplied by the average velocity. The instantaneous power is equal to the product of force by velocity. In addition to the unit watt in the SI system, there is another unit that is used in the British system, which is the horsepower. 1 HP, 1 horsepower, is equivalent to 550 foot-pounds per second, and this is equivalent to 746 watts. Another unit that we use for energy is the kilowatt hour. 1 kilowatt hour means this product. So when you evaluate, this would be 3.6 by 10 to the power 6 joule. This is the unit for energy that we use to measure the consumption of electric power at our homes. Okay, if you check the bill from the electric company, you will see the energy consumption expressed with a number followed by kWh, which is kilowatt hour. The last part of this chapter is about energy and power in a vertical jump. This is just an example. So here, imagine this situation. The center of mass is the point where we can treat as if the whole mass is located at that point. So here, before the jump, the velocity of the center of mass is 0. As this guy jumps, starting moving, so the center of mass moves up. At maximum height, the velocity of the center of mass is 0. The energy is all potential. Initially, the energy was all kinetic. So applying the energy conservation principle, we can solve for h, the height. It is equal from this equation, divide both sides by m, and solve for h, the height of the center of mass. It is v center of mass squared divided by 2g. Now for v center of mass, we can calculate that from, or estimate that, I shall say, from the average velocity. It is twice the average velocity, and the average velocity can be calculated. The assumption here is that this distance for an average male adult is 0.4 meter, and it takes 0.25 seconds for this jump. So from there, we can estimate the velocity of the center of mass. It is 3.2 meter per second. Therefore, h can be calculated or estimated, I shall say, 3.2 squared divided by 2 by 9.8. This is 0.52 meters. That would be the average value for a jump by a healthy male adult. Now, the energy involved in such a jump, you need to calculate the kinetic energy, half mv center of mass squared. For a healthy male adult, average mass is 68 kilogram multiplied by the velocity of center of mass squared. This is equal to 350 joules. 350 joules. The efficiency of energy transformation for humans is at best 25%. The remaining 75% is just wasted energy. So if you apply the efficiency, if you take the efficiency into considerations, this guy invested 4 multiplied by 350 joule, which is 1400 joules of energy when he did this jump. Now, one food calorie is equivalent to 4200 joule. This means this jump costed this guy 1400 joule divided by 4200 joule. This is 1/3 of a food calorie. This gives us an idea about when we exercise, about the energy that we consume during exercise. Power is energy per unit time, so you need to take the energy 350 joule divided by the time involved, 0.25 seconds. So the average power is 1.4 by 10 to the power 3 watt. That would be the average power. You can convert that from watt into horsepower using the conversion factor. This is 1.9 horsepower. From this table, we see that for human activities, the power, it drops with time. Like here, the first 6 seconds, the power, which is the energy rate of consumption over production, 1500 watt. After 16 seconds, it dropped to 750 watts. After 8 hours, it drops to 75 watts. Okay, this is the safe daily level of energy that we can provide with our activities.